Hey y'all, let's do some work. JRandom Troll is helping Susie move. He pushes a box with a force of 250 newtons for 10 meters. How much work does JRandom do on the box? Well, I know that work is the integral of force with respect to distance, and I know that the distance is going from point 0 to point 10. So I set up my bounds of integration as from 0 to 10, and now I'm just going to execute this integral real fast. It's not too difficult because the force is constant. Whenever you have a constant inside an integral, you can just pull it out front, and I'll end up with force dotted with the integral from 0 to 10 of just 1 dr. Okay. Well, that's a pretty easy integral to take. It's just r. So this becomes force dotted with r from 0 to 10. Now, since he's pushing it to the right and the box is traveling to the right, that means the cosine of the angle between them, here, I can even write this a little bit differently. I can write this FR cosine theta, where r goes from 0 meters to 10 meters. Okay? Well, here, theta is just going to be 0 degrees because both vectors are pointing to the right. So it simply becomes F times R. So that's going to be 250 newtons times 10 meters minus 250 times 0. I don't even need to write that because 250 times 0 is 0. And I end up with the work that he's done being just 2,500 joules. Here, I'm going to run into the Doceri watermark if I go that way. So let me say 2,500 joules. Well, while JRandom's helping her move, Susie utters a snide comment, and let me tell you, this was a nasty, nasty statement, and I cannot repeat it as a teacher in a public school. But it was pretty nasty. So JRandom decides, forget this, and he just gives it a big old shove. He pushes that box and he lets go. If the box slides 3 meters across the floor and then stops, and it had an initial velocity of 5 meters per second, how much work does friction do on the box? And what is the coefficient of kinetic friction between the box and the floor? Well, since it's just on a horizontal surface, I know my normal force is mg. It's on a horizontal surface and there are no additional y forces acting. So I can replace normal force with mg. I can find the force of kinetic friction as the coefficient times mass times 9.81. But, I was not given the coefficient of friction. In fact, it asks me what that is, so I can't solve for the force of friction right off the bat. All right, let me look at it another way. I know that the total work done on an object is the change in the object's kinetic energy. And I also know that since this object had a force of gravity, a normal force, and a force of friction, that the only force doing work here is friction, because normal and gravity are canceling each other out. So I could say that the force of kinetic friction times distance is equal to the change in kinetic energy. Let me just solve for the work first. So looking at the change in kinetic energy, the final kinetic energy is just 0 because the box comes to rest. The initial kinetic energy is going to be 1/2 times the mass times the velocity squared. So the total work done is going to be negative 125 joules. It makes sense to me that this is negative because kinetic energy is being removed from the box by friction, so negative work is being done. All right, well, now that I've got the total work that's done, and I know that the total work is from friction only, I can set the total work equal to the integral from I don't know my bounds yet. Oh wait, just kidding. Yes, I do. It traveled 3 meters. There we go. So from 0 to 3 of the force of kinetic friction times, or dotted, sorry, this is a vector dot product, dotted with dr. Okay. Well, I know the force of kinetic friction is constant, whatever it is, so I can pull that outside, and this integral just simply becomes, if I skip a couple of steps here for the sake of time, the force of kinetic friction times 3. Although this time it's going to be times the cosine of theta, and since the box is traveling to the right, but friction is pulling it to the left, I'm going to use 180 degrees for theta. And the cosine of 180 degrees is -1. So this will become negative force of kinetic friction times 3. So that gives me the force of kinetic friction is going to be -125 over -3. A joule is the same thing as a Newton meter, divided by 3 meters. My unit of meters cancel. I end up with the force of kinetic friction being 125 over 3, which is 41.7 newtons. Right? And now that I know that the force of friction is 41.7 newtons, I can set those 41.7 newtons equal to the normal force, which I know to be mg, times the coefficient of friction. So I can find the coefficient by simply taking 41.7 newtons and dividing it by mg. Since it's a 10 kilogram block, this will become 98.1, and I get a coefficient of about 0.43. And Susie Cream Cheese apologizes, J Random Troll accepts, and they decide to be friends again. To celebrate that continuation, they go and play in the snow. They forget about moving and just go and play in the snow. Susie sits on a sled, and J Random drags it, pulling on the rope with a force of 300 newtons at an angle of 30 degrees, and the sled slides horizontally for 5 meters. How much work did J Random do on the sled? Once again, I'm dealing with a constant force, so the work done by J Random is going to be the force times the integral from, in this case, my bounds are 0 to 5 of dr, and that'll ultimately be, work would be the force, 300 newtons, times the distance, 5 newtons, times the cosine of the angle between them. In this case, that angle is 30 degrees. And it's 30 degrees because the sled slides perfectly horizontally, and the force is 30 degrees offset from the horizontal. So I get the work that J Random did on the sled is 1,300 joules. Now this doesn't mean that's the total work that was done on the sled entirely. I wouldn't necessarily set this equal to the change in the sled's kinetic energy, because odds are there's a little bit of friction between the sled and the snow that was doing negative work at the same time. So if I found the work that friction did, then I could find the total work done and set that equal to the object's change in kinetic energy. But I don't have enough information about the friction to do that with this problem. Now, in the 3 examples I've done so far, you've dealt with a constant force. Well, what if the force isn't constant? And I thought about a couple of ways of going about this. I could give you a function, f of r equals 3r, but then you would just simply take the integral, find the new, the expression for work, and then sub in your distance values there. But I thought I would look at it graphically as well. We haven't done a whole heck of a lot graphically yet. This one shows a force exerted on a 2 kilogram object as a function of the distance that the object travels. The object is at rest at d equals 0, and it travels on a horizontal frictionless surface along the line of action of the force. Great. That tells me theta is 0, because the force and the movement are in the same direction. So what is the work done on the object by the force during the first 10 meters of travel? So we're going to cut it off right here. We're only looking at the first 10 meters of travel. Right? Well, I know that in this case they use d for distance. We've used r. It's all the same thing. So I could write the work as the integral of force with respect to distance. Cool. Now, you've probably hit this in your calculus class, or if you haven't, you will soon. But when looking at a graph and taking the integral of y versus x, what's on the y-axis versus what's on the x-axis, the integral is simply the area under the curve. So all I need to do is solve for this area right here. Okay. To do that, I'm going to divide it into two different sections. I'm going to find the area of this triangle. Then I'm going to find the area of this rectangle and add those two areas up, and that would be the integral of force from 0 to 10. Cool. Well, the area of a triangle, I'm going to start with the triangle there. Area is base times height. So the base of the triangle is 5 meters. The height of the triangle is... Whoa! Area of a triangle is not base times height. Good Lord. The area of a triangle is 1/2 base times height. That feels better. Okay. Well, 1/2 times 5 meters times 10 newtons is going to be 25 Newton meters, or 25 joules. The area of my rectangle is base times height. And let's see, I've got a base from 5 to 10, that's a base of 5. I've got a height of 10 newtons, so that's going to be 50 joules. 50 Newton meters or 50 joules. So in total, the work done from the first 10 meters, or work done over the first 10 meters, is going to be 25 plus 50, that is 75 joules.